morning, Ashutosh. Good morning, Prajwali. Atharva, good morning. Achal, good morning. Anuja, good morning. Mayur, good morning. Tejas, good morning. Kriti, good morning. Muskan, good morning. Dhruvesh, good morning. Mitali, good morning. Nikita, good morning. Yoga, good morning. Manjiri, good morning. Rasika, good morning. Purnima, good morning. Rajiv, good morning. Sarthak, good morning. Avinash, good morning. Chinmay, good morning. Viraj, good morning. Asmita, good morning. Pranav, good morning. Vaishnavi, good morning. Akshata, good morning. Aditya, good morning. Good morning to all of you all. Manasi, good morning to you as well. Well, someone else. Rutuja, good morning. Oh, Anjali, good morning. Second Anjali, good morning. This is Anjali Gorve, Anjali Kumari, Bini Thakur. Good morning to you all. Okay, a few things first before we go on to what we are supposed to be doing today. That a lot of students are joining anew, so I would request some of y'all to repost a few things. In the sense, the syllabus for the students needs to be reposted, both physical and human. Besides that, the reference book, the links for the books need to be reposted. So I would say once in a week we should be doing that, because I hear that students are leaving from BSc and joining engineering. Students from engineering are leaving engineering and coming to pure sciences, that's BSc. So we'll have to go by them, and they keep calling me, or rather messaging me individually. I have informed them that students will be posting the details accordingly. So that is one thing. Secondly, a lot of regular students also have started asking me about the syllabus for the first semester of geology. Yeah, and as far as that aspect is concerned, Pragati, good morning. Uh, Everything that we are doing regularly and upcoming Yeah, sorry for the break in connection. I shifted to some other connection. Prathamesh, good morning. Tushar, good morning. So, what we are going to do is all going to be available. Yeah, Radhika, good morning. Akshata, yes, I've shifted to a faster connection. Possibly we should not be having these issues for the rest of the lecture. Let us see how it functions. Yeah, Achal, I know I have corrected it. Let us see how these things would change. Okay, Maitri, good morning. Sahil, good morning. So, possibly, Abhishek, good morning. Possibly the first two topics should be covered by the time we go to that particular thing. But something that is very important with regards, so to say, geomorphology as a core subject, because you'll see that when I look at geomorphology at the PG level, it is more intense as compared to introduction to physical or geomorphology, physical geography or geomorphology at BSc level. So it may so happen that not everything that needs to be covered in geomorphology is done with y'all, because the syllabus restrict ourselves to that extent. But then there are a few things in geomorphology. If any student should be knowing that, they would be finely placed as far as understanding, say, the connecting dots as far as the whole philosophy and the study of geomorphology is concerned. So what I'm trying to do is today is that I would have I have this PPT which I borrowed from SlideShare, and we would be running that today, and I would be explaining it to you so that we link all the dots as to what is required for the study of geomorphology as such. And without wasting much time, I would shift to that. And yeah, let me share it with you all. Here it is. This possibly is a slide that we have seen earlier as well. And these are the various features that you would see as far as geomorphology is concerned. You'll see that this is basically the various forms of water, okay, and how water is impacting this particular planet, right? From a lot of water, okay, in the left side, to solid water, left, down, and then of course the sea waves, and towards the right side you lack of water, that's deserts as such. So it's all about this that we primarily look at as far as the human naked eye is concerned. But there are a few more things that are connected to geomorphology, and we'll go to that one by one. We have done a few things before, but I would repeat them for the sake of the new students as well. I will just reduce the size of this so that we are able to watch the whole slide in one picture. The word geomorphology has a Greek origin. Geomorpho and logos basically means the earth and the form of the earth, and of course the study of these forms on the earth. So geomorphology is basically study of earth forms. I would say more on the land particularly, because whatever lies on the crust but beneath the water surfaces is taken up as a study in oceanography. So that is one thing that we have to remember, that features like continental shelf and continental slope, etc., would be studied in oceanography, not in geomorphology. Geomorphology is everything related to land, everything which is not overridden by water will obviously be land. And let me tell you, the encompasses of the land sphere or the water sphere will change according to the rising or the lowering temperatures, in the sense that if we are going to have, so to say, a greenhouse effect, and ice is going to melt, is what is believed is happening today, then the poles will release a lot of water from the ice, and this will cause a lot of rise in sea levels. So the amount of land available is going to be less. On the other extreme, if you're going to have an ice age, this ice forming during the ice age is going to consume a lot of water, and so the levels will fall down. So this has been happening throughout the history of this planet. But we have to remember that whatever is above the mean sea level is going to be land, and whatever goes beneath that is going to be submarine relief studied in oceanography. Geomorphologists, as I've just said, are concerned primarily with Earth's superficial features. Okay? And what we do in that is we try to establish a theory about their origin, their history, their composition, and more so, why do we do this as human beings? You can see that other animals are not studying all these things. Okay, obviously a question would be, why are we as human beings studying this? Basically, we need to study this so that we know the impact of this on human activities as such. And of course, conversely, human beings also have an impact on these features. So we study both of these together. Geomorphology particularly studies more of say the quaternary period. Okay, if you remember when we did the geological time scale, We spoke about the Paleozoic, we spoke about the Mesozoic, and in the Cenozoic, we divided the Cenozoic into tertiary and quaternary. Tertiary, if you remember, is the period wherein the Himalayas went into formation. Holocene is when man comes into picture. And as far as this aspect is concerned, uh, whatever has happened to the earth in after man has come onto this particularly with reference to river flows, etc. Okay, you'll see that's a very interesting thing to be studied. So that is obviously being studied as far as modern geomorphology is concerned. So that is the focus of geomorphology, I would say. Earth landforms, you'll see that they reflect the local and the regional balance between hydrologic, tectonic, aeolian, glacial, atmospheric, and marine processes. Now, of this, how much are related to geomorphology? Hydrologic. Now, you would say that, sir, you just said that hydrologic, water is not related to human beings, but then, as far as study of geomorphology is concerned, but then let me tell you, this hydrologic includes rainwater. Okay, so the water cycle is going to be an important part. Tectonic, in the sense, plate tectonics, affected by the forces from the inner aspects of the earth, the interior of the earth, which we partially did, I suppose. And aeolian, of course, aeolian is airborne. Aeolian basically means airborne. So all those areas wherein you don't have water as an carving agent of the surface, you will see that air will take up its function of carving out land features on the surface. And then glacial, solid water is a glacier. Atmospheric and marine processes. Marine processes, we saw one of the photographs earlier. Coastal waves, etc. How they carve out landforms. You'll see that beaches, cliffs, and caves, etc. All that is included as a scope of geomorphology. Why do we study geomorphology? The importance of geomorphology, you'll see that it is to understand the processes in various environment. Okay, you'll see that water environment, solid water environment, mountainous environment. We could just shift a bit to various climates. You'll see that the same amount of processes, but in a different climate. Okay, they will impact the land features differently. Say, for example, if we study about weathering, something is you may have done in an earlier class in your school days. As such, you'll see that chemical weathering is more seen in equatorial regions, but physical weathering is more seen in where you would have a lot of ice, that's very cold temperatures, as well as the fact that where you have very hot temperatures as such, because very cold and very hot temperatures not only affect the surface physically, but they limit the chemical activities. So chemical weathering is there. You'll see that as far as equatorial regions are concerned, in equatorial regions you'll have a lot of so to say humidity, and you have water, and the temperature from the sun keeps it very humid. So it's a perfect scenario of a chemical lab, a natural chemical lab. So you'll see that with different climates, the same set will operate differently. A river in the equatorial region would be different. A river in an arid region would not be a perennial river. Okay, a river in a cold region, okay, so the taiga region would freeze during the winter of that particular region. So the same things, but when they operate in different climates, they will show a different geomorphology, not different geomorphological process, but an output is going to be different of the same geomorphological process as such. Then, more importantly, while we do all this, what do we detect along the way while we are studying this? We detect natural and environmental hazards. Natural hazards would mean basically where possibly are earthquakes going to happen, where possibly are volcanoes going to erupt. Okay, it's only when we understand all these things that we would be able to protect human life and human property also. Okay, and environmental hazards also. So, for example, tsunamis and other sorts of pollution, flooding particularly, all these can be easily detected if we are thorough and through with our study of geomorphology as such. So the more thorough and through we are, the more easy it is to detect and demarcate the regions where you could have earthquakes and the other things that you can find in front of you. Then, to identify identify various landform features and landscapes. You'll see that various landform features and landscape respond differently. So we need to know whether that is an erosional feature or whether that is a depositional feature of these things. Okay. Nowadays, of course, this has been put to practice by use of satellite images, because many a times you'll see that landforms and landscapes are very, very large when you compare the human size to it as such. Now, so for example, if I'm studying the Himalayas, it would take months for me to walk from one corner of the Himalayas to the other. So a satellite image of the Himalayas is easier. I can sit on the table, I can put the image on the computer, and I can analyze what is happening as far as the Himalayas are concerned. And in fact, if I have a satellite, what is the most important function of a satellite is that I can do live streaming, and I can have those just like a security camera in a particular campus. You'll see that you have many cameras, right, in one particular screen. So you could put up such cameras or such focuses of the satellite, and at one time you could be looking at various regions of the Himalayas. So that's the advantage that satellite technology has brought us to, which after which you have coastal and river research, because as far as coasts are concerned, on a very superficial level, of course there are other areas of research, but on a very superficial level, you'll see that nearly 40 to 45% of the population of the world is in coastal locations. So to protect the human life and property, we have to understand the coastal landforms, etc., and coastal environments particularly. We just spoke about a tsunami. Okay, so with 45% of the world population having coastal location, a tsunami could be very disastrous. At the same time, river research is important, because rivers, they carve out their floodplains. It is on these floodplains that we cultivate our crops, and we feed on these crops. On the same aspect, you'll see that rivers supply us with a resource that we require very regularly, and that is water. Okay, so again, coastal and river research is important. Vulnerability studies. The second point did discuss about it, but just needs to be identified separately, that how much population is vulnerable. We just said that tsunami makes the coastal areas vulnerable. So which area in the coastal region is going to be vulnerable? All these studies come up in geomorphology as well. And of course, it connects various subjects together, say geology, geography, archaeology, engineering. If you're constructing a highway, or if you're constructing a dam, or you're constructing a resort in a coastal area, engineering, planning, mining, construction, urbanization, all of this is connected to the study of geomorphology. One of the reasons why we study geomorphology as such. Okay, we don't have to go into the details of this. We have just gone into the details of this a few weeks ago. But yes, the geological time scale forms a very important part of the study of geomorphology. We know that from Archean to Proterozoic, and then the larger forms of life, that's the older life, Paleozoic, the medium form of life, that is the Mesozoic, and the modern form of life, that is Paleozoic. And the Quaternary, let me tell you, involves the upper two, the Pleistocene and the Holocene, is the Quaternary period. We just saw that the geomorphology focuses more on the Quaternary period. So that's the upper two. Okay, so we are not, geomorphology does not go much deep unless and until the requirement, the study requires. So otherwise, you'll see that it's just the last few thousands of years as far as the scope of geomorphology is concerned, because it's dynamic. It needs to know what is happening around human beings right now. That's the scope of geomorphology. Then, as I said that, say for example, we have this photograph in front of you. Now, many of you all would say that, well, this seems to be placed there. But let me tell you that this is not a rock which has been placed there. It has been there as it is for possibly thousands of years before it was detected there, and since then it has been staying there. So what past processes created this relic landscape? You'll see that you have a flatter surface down, and then you have this rock standing up on that. What modern processes are modifying it? Okay, so what happened in the past? Now, looking at this, you'll see that as far as carrying this large rock is concerned, and given what you have at the base of it, It's very, and of course, see how a geographer needs to identify all these things. Looking at the trees behind, you'll see that it is a colder region. It's a temperate region. So possibly temperate region means at some point of time in ice ages there could be glaciers here. So while the glaciers retreated the deposits from these glacier, this is a huge rock and it has stayed there. How I can confirm it could have been a glacier? You'll see that the flat surface that you have there, that's the original surface. The glacier moved on this, and then what fell into the glacier has slowly sunk down to the base of the glacier, and it has been left where you can see this in a photograph. Okay, what are the modern processes modifying it? Possibly 1,000 years out from now, the heat, the water, the chemical actions of insects and the trees growing around, the leaves falling on it, may disintegrate and decompose this rock to a smaller size. Possibly it was a larger size earlier, but now you'll see now that it's soft. You'll see that a rock which has soft sides obviously has faced a lot of aberration, I would say, friction. That's I would say a rock which has a lot of edges, I would say, is a modern rock. So this comes to be known only when you are studying, so to say, geomorphology. Okay, where were the processes that created the relic landform destructional or constructional? What are destructional processes? What are constructional processes is something that we need to be very clear about, and that's why this particular lecture, unless and until we are clear about what constructional and destructional processes are, we tend to get confused, because let me tell you that what we understand as destructional is different as to how geomorphology looks at it to be destructional, and vice versa. What we understand as constructional is understood as destructional when from the focus of geomorphology as such. And these are a few things that we need to keep in mind when we are studying geomorphology. So even if you study a small part of geomorphology, but you know the core of it, you can do the rest of it without any tutoring help as such, without any teacher as such. Okay, my focus today is going to put all that together for you in this lecture. Let us see how far we can go. Are there modern processes modifying this landscape? And these modern processes, are they again destructional or constructional? We need to look into that as such. Okay, this is of course not for us. Yeah, this is something which is not a part of your syllabus, but as I said, that when we understand geography, when we understand geomorphology, there are a few things that we need to look into, in the sense that we spoke about the scale. Okay, when we speak about geography, we speak about scale. It's the proportionate size of an object in nature and how you place it on a map. Okay, so when you are drawing a map, like you can see here, is basically drawn to a particular scale, and that is why it looks like the US, the map of USA. Had it not been to the scale, let me say that I would not have been proper towards the right side, and I would have been improper as far as the left side is concerned. It would look something very weird and different. That's why our scale is very important. So when we are studying geomorphology also, we have to keep the scale in mind. And these scales have an order, right from order number 1 to 10. The 1 basically means the largest form, and 10 basically means the smallest form. Okay, and this becomes important basically to get reference. Okay, how do we refer to each other? Or otherwise, it may so happen, just like it happens in time scale, that a person on one side of the earth would be referring to time in the morning, and a person on the other side of the earth would be understanding it as evening time. Okay, somebody says meet me at 6 o'clock. Somebody would wait right in the morning, but the person who is told, maybe he's anticipating the evening time. Similarly, we need, when we understand the geomorphic features, we need to be very clear about the scale. So largest of the scale, okay, which could be 10 raised to 7, say 10 raised to 7. 7 zeros, basically, if you remember, we simplified this. This is 1 crore square kilometers. Now, what could be the size of 1 crore square kilometers? Obviously, continent or ocean basin. It's only that could be so large. Okay, because you'll see that as far as India as a country is concerned, if you see, if any one of you can remember, I'm not asking as a question as such, but just think, can you immediately come to the context of the area of India? You'll see that it is 3.2 million square kilometers, 3.2 million squares. Now that is 3.60 square kilometers. This is 7 zeros. So obviously something larger than that. So the largest of these scales is land and water. What we call land we call as continent, and water we call as oceans. So the largest of the scale. How long does one continent or an ocean basin exist? Okay, is what you can see towards the right side of your screens. That's basically the time scale of persistence in years, 10 raised to 8 to 10 raised to 9. Okay, so this is billions of years put together. A continent will be there for billions of years. But when you come down, 10 raised to 6 physiographic provinces, 10 raised to 4 medium-sized tectonic units, sedimentary basins, mountains, etc. So on from a mountain, which is continent, which is 10 raised to 7, we come down to 10 raised to 4. 10 raised to 4 is 10,000 square kilometers, let me tell you. Three zeros is 1,000 and 4 zeros is 10,000. So medium scale tectonic units. How fast do they change? You'll see that the years have come down. Okay, you'll see that 10 raised to 7 or 10 raised to 8. So that's just a few crores. And we know that the Himalayas are around 6 to 7 crores of years old. So this is how we tend to match up things as such. The larger area and the amount of time for which they tend to be in existence as such. We go down. I will not go into every scale. I would in fact urge you all to go into the details of these on your own and try to understand how slowly we go down and down and down. Okay, so for example, 6 is that we are going below the positive. In fact, we have started moving into the negative scale. Okay, so from kilometers, we are going to go down. See, floodplains, alluvial fans, moraines, small valleys, etc. They are not kilometers wide. They are a few hundreds of meters wide. And you'll see that the speed at which they change also is faster. You'll see that they could change in a few, say less than a million years, a few lakh years, I would rather say, is how they would change. Okay, so further down, you'll see that erosional and depositional features, ridges, sand dunes, etc. And the lowest one on in the 10th order, you'll see that micro scale geomorphic processes. Okay, you will see that ripples. You must have seen these movies of deserts, and you have a desert storm. I think Mission Impossible, one of the series of Mission Impossible had that desert for storm in that. Okay, you'll see that what picks up that what picks up that particular storm. It's going to be small, very small grain size. It could be grains of sand. It could be millimeters, and that is why it is 10 raised to -8. But you see that we geomorphologists would be interested in a scale right from 10 raised to 7 to 10 raised to -8. So that is the scope that a geomorphologist has to look at. And the speed and time, you'll see that from billions of years where nothing tends to happen for a surface, microseconds wherein these sand particles could be traveling from one place to the other, at times meters, at times kilometers, horizontally and vertically. That dust storm itself, I don't know how many of you all have watched that movie. That's Mission Impossible, wherein that particular sequel of that title had a dust storm in that. But you'll see that when a dust storm, or you can imagine any other dust storm as such, when it picks up, it's not very close to the surface. It glows up into the air, isn't it? So at times it could travel a few kilometers into the air also. So vertical expanse, horizontal expanse, all of this contributes to understanding classification of terrestrial geomorphologic features by the size, by scale particularly. Scale in the sense the left side is a spatial scale. How much space does that particular unit of landform occupy? And right side is the temporal scale, the spatial and temporal. If you remember these two terms, we had done in one of our first couple of lectures as such. Spatial is anything that occupies space, S-P-A-T-I-A-L. Let me remind you, some students will pronounce it as spatial. It is not spatial. The T is silent here. You pronounce it as spatial. And the scale of time is referred to as a temporal scale. So this is one of the most important slides, I would say, a geomorphologist should be carrying. Okay, then we move ahead. It's an explanation of the same thing. Okay, scale of landforms, age of landforms. Larger landforms are most durable, longer lasting. That's what we have already said. Rates of geomorphic and geological change are slow for larger areas. Okay, while the smaller ones happen faster. Now, this is something that we have done earlier as well. The rise of geomorphic thought, we have spoken about Herodotus and how and what Herodotus did speak about. If you don't remember, I'm going to come to that. And then after the initial few, you'll see that there is a slack as far as geomorphological thought is concerned. And then you come down to the 17th century, and then you have Hutton, and then you have the 18th century, you have Agassiz, you have Powell, and you have Gilbert. What are they going to speak about? It's very interesting coming to that. And then you have the correlation, how you correlate something. Okay, you'll see that how it changes. Okay, from in ancient times, geomorphology was just observation and trying to put up hypotheses. Then you come to the 17th century with a gap of nearly 2000 years. You come to somebody who's describing what is things happening. Okay, and a description is very subjective, if you all know. Okay, if I ask you to write an answer of 250 words, 500 words, okay, these words would not be same. But if I have an MCQ for you, multiple choice question for you, the answer has to be that very option, isn't it? So subjection, okay, is very, very relative, right? Objectiveness is pinpointed. And then you have explanations to these processes. People try to explain that, okay, this must have happened in this way, this must have happened in that way. Then comes Davis, okay, the cycle of erosion, and he tries to correlate things. That's a river, he tries to correlate it with something else as such. Now, of course, quantification and prediction, that if this thing is happening in so many years, the larger thing will happen in so many years as such. So that is what is quantification and prediction is all about. Okay, this, if you go into the details of that, you'll see that Herodotus speaks about, say the rocks on the land of Egypt, particularly along the coastline, had marine fossils. Okay, so he hypothesized that the Nile Delta must have taken thousands of years to form. Okay, followed by Aristotle. He says that dry land can be submerged, and he described erosion by rivers and so on and so forth. And then you have Sena and you have Ibn Sena in between. Okay, Ibn Sena concluded that mountains could be uplifted and later eroded. Okay, so that's a very interesting observation. That was made 1,000 years ago. Then in the 14th century, you have Leonardo da Vinci, who found marine fossils on land. So possibly concluding that what seems as land today at some point of time could have been underwater, and thus you have the marine fossils on land as such. And then you have Bauer, who hypothesized that mountains were sculpted by weathering and mass movement as such. Steno, he regarded water as the most significant agent of erosion. Okay, and that is how we slowly come to Werner, and you have Georges Cuvier, okay, who speaks about using unconformities and so on and so forth. We're coming to that. But then, as I said, that around the 17th century, you have James Hutton, okay, and he brings in the theory of uniformitarianism. Okay, I think we did this earlier, but we need to repeat it again, that the processes that carve out the land surfaces, is what Hutton says, are uniform, and they tend to be uniform throughout the surface of the age of this particular planet, right from the formative age, with a few things here and there. Okay, the basic laws of science have been the same. So say what happened in the past is happening around us presently, and of course it will happen even after we may not be on this particular planet as individuals or as a species of animals as such. Okay, that is what basically, that's the nutshell of what James Hutton had to say. Okay, processes are gained by what is called as uniformitarianism. What has happened in the past is happening around us right now, and will be happening around us in the future as such. If it was raining then, if it's raining now, as it has rained in the past, it will rain in the future. The only thing that would be dynamic is, let us say, the acidity of the rain. Present pollution may cause more acidic rain in the future, but we may have lesser amount of rain, acidic rains in the past. So the processes are the same, but there are a few dynamisms as far as these processes are concerned, is what James Hutton had to say. Now, why is this important? Basically because before James Hutton pushed forth the theory of uniformitarianism, you'll see that there was a theory of catastrophism. Okay, that means that geomorphologists before that, they believe that everything that is being formed around us, it is catastrophic. in the sense it's sudden, okay, and it's huge that it's forming around us. Okay, now there's the obvious logic why people thought like that before Hutton was the fact that they had experienced earthquakes, sudden shaking, and all the destruction of the earthquake. Also, they had studied, they had witnessed rather volcanoes. Okay, again, all of a sudden and causing a lot of disaster, a lot of sound and energy, and because of that, they said that they thought that all these formations, and at times, of course, these shooting stars, etc. So they believed till Hutton said so that everything around them was catastrophic, and thus you'll see that the contribution of Hutton when he says that no, it's a uniform process, and I advocate uniformitarianism is what changed the face of geomorphology. Okay, ever after that, we are looking at geomorphology from an uniformitarianism focus rather than a catastrophic focus as such. Okay, so that's the contribution of Hutton. Okay, yes, here you'll see uniformitarianism. Scientists make observations of events, and they try to explain those observations by organizing them into a logical system. Yesterday, today, tomorrow. It could be modern river channels, it could be ancient river channels, because they were the same when it was past, and they are the same when it is present as such. Okay, so that's uniformitarianism. You see that Hutton was, say, after Hutton, okay, he had his followers who very seriously looked into this particular aspect. Okay, you'll see that Playfair. These are important names when we come to physical geography as such. Okay, you'll see that Playfair brought in the concept of a graded stream. We are not required to go into the details of that. We just have a diagram later. Let's see if we can how say address to that. Then you have Charles Lyell. Lyell speaks about he speaks about uniformitarianism in a very serious way. In fact, he denies and he discards the theory of catastrophism very seriously. Okay, so both of these, okay, Playfair and Lyell, are supporters of Hutton's concept as such. Okay, and then you have this particular thing happening. Okay, you have Bennett's, and then you have Agassiz, but most importantly you have Charles Darwin. Charles Darwin, of course, is not a geomorphologist, he's not a geographer, but you'll see that in his voyage of the Beagle, he is known to have suggested the origin of the atolls, and that is why those who study oceanography are well known to Charles Darwin, because the theory of formation of atolls in oceanography is given by Charles Darwin. What is more important about Darwin is that his theory about evolution and his statement about survival of the fittest and so on and so forth. Okay, you'll see that Darwin is born in 1809, and he lives up till 1882, and he just say blankets the world with his thought of evolution and survival of the fittest and so on and so forth, looking at every organism as young, adult, and old, and so on and so forth. So the world was dominated by the thought of Darwin, and obviously he had to have his impact on others as well. Now you'll see that this is 1882, 1809, and 1882, and you'll see that W.M. Davis, the person who gives us the cycle or river cycle of erosion, okay, he is born in 1850. So possibly when Darwin was at his peak, when Darwin is at his peak, Davis was a very young person, and he was looking and studying what is happening around him as such. So he bases his cycle of erosion as far as the river is concerned on Darwin's evolutionary theory as well. Okay? He says that landscapes keep on evolving throughout time. It's not that they have happened and they stay there as they are. Okay? They change. It's very dynamic. And then the stage of evolution can be determined by examining the characteristics of the landscape. And one more thing, he implies time as a critical factor in determining what landscape looked like. Okay? This very famous statement by Davis. He says that any landscape is a function of structure and process, okay, which for a given period of time. landscape is a function of structure and process in time. Okay, now what is structure? Structure is what makes up that particular feature. Process is what is carving out that particular feature. And for how much time it is into formation, the structure, for how much time the process is operating, it is the third aspect to it. And all of this will result into a landscape, a feature as such, is how W.M. Davis he speaks about how geomorphology goes about these things, and this gray area in the center is basically an overlap of all three: structure, process, and time. Is the resulting landform is what he says as such. Okay, so structure is the rock mass basically, process is the constructive or destructive process, and time is the landforms evolve through steps and stages for continued action. Okay, so that is what he has to say. And here Davis speaks about the cycle of erosion. Okay, he says that structure, say it could be an earthquake or it could be a volcano which evolves up a landscape, and you'll see that water starts operating into that. It goes mature, and then finally it goes old as such. Okay, so uh, that is where he relates it to say the cycle, the human cycle or life cycle, you'd say that just like, and here is where we can connect the impact Darwin may have had on Davis as such, because he looks at a river which otherwise seems so abstract as young, mature, and old. Okay, a river has to pass through all these three stages as over the period of time, let us say. So that is as far as Davis is concerned. Then you have Gilbert. We don't have to go into that the aspect, but then, as I said, that he speaks about a graded profile. If you remember, I said about this a few minutes ago. And as far as this graded profile is concerned, he seems to be having a stage of equilibrium between the driving forces and resisting forces as such. Okay. Now the Davisian geomorphology and time as the uh, factor dominated the scientific literature until 1960s. In fact, it is believed that till 1940, everybody was with Davis. Now, of course, you read books and you would have the drawback of Davisian theories as such. But till 1940, there was nothing as called as the drawback of Davisian. Everybody said that yes, what Davis says is absolutely right. That is the impact Davis had on the geomorphic and the geographic scenario. And that's why when we speak about Davis, amongst the first 10 words that 10 scientists that we list in the study of geography, Davis tends to be one of the first of these. As okay, 1930s to 1965s, you have the rise of what is called as quantitative approaches to geomorphology. You quantify everything. If you have a deposit, you quantify it. If you have an erosion, you have quantified. And these quantitative trends have continued further with the use of computers, because computer programming has made quantification much easier. Satellites are being used. Okay, remotely sense data, numerical methods, improved data dating techniques have all put together to and enriched the study of geomorphology and physical geography as such. We could have this the types of geomorphic equilibria, but let us not go into this because this is a bit for postgraduate students and not for you all. I'll skip this. And here we come to the concept of equilibrium. Uh, you'll see that because a river is so easily understood and seen by a majority of the people, it so happens that um, the processes of geomorphology are many a times explained using a river as such. So when you look at a river, what do you think of? You think of erosion, you think of transportation, and you think of deposition. Now you have to ask yourselves a question: why does a river erode at one of its end, and why does the river deposit at the other end? It's basically for the sheer purpose of attaining equilibrium. Okay, and once the equilibrium is achieved, you see that the function of the river is done, and the river will go extinct. Okay, so very similarly, you'll see that in fact you'll find the way why all these concepts are important, basically because they come out of the theory of Darwin. Okay, in fact, you'll see that as far as human beings are concerned, you'll see that you breathe, I am breathing on my side, you are breathing on your side, you are breathing your own share of air, I am breathing my own share of air. But have you ever imagined that it's so very a natural process? We don't apply energy to do this. Yes, we lose a bit of energy, but you'll see that it's not say loss of energy as much as when we are running and so on and so forth, because it's a natural process. Okay, and how does this natural process work? It's basically based on pressure. Okay, and there is an inequilibrium in the pressure as such. What is this inequilibrium? You'll see that when I'm inhaling, what is happening is that the pressure outside, the air pressure outside is more. You have high pressure out, and in my lungs I'm going to have low pressure, so the air is going to travel into my lungs. But while I have inhaled, what I have done, I've created high pressure in my lungs, and I'm going to have low pressure outside, so I'm going to, okay, exhale out of it. Okay, so the inhalation and exhalation is basically because of an inequilibrium that exists in nature, and it exists within as far as the process of respiration is concerned. As a consequence, now just imagine what would happen if there would have been an equilibrium. If had there been an equilibrium, we would have stopped breathing. And what happens when we stop breathing? Obviously we would have died. So you'll see that majority of the processes around us, okay, it could be life cycle, it could be physical cycles, it could be chemical cycles. Okay, they happen basically because there is an inequilibrium. Okay, when there is an equilibrium, the process is near to getting subsided as such, or getting extinct as such. Okay, so that's a very important meaning of equilibrium that we have to consider here. Otherwise, in science, and of course with reference to geography also as such, geomorphology refers to it as no net change. Okay, you'll see that where neither erosion takes place, neither deposition takes place, everything is equalized as such. Now, this happens. You'll see that the base level of erosion is supposed to be the mean sea level. You'll see that rivers tend to erode land, and they stop erosion. Or why do we have deltas near the mouth of an ocean? It's basically because there where an equilibrium is set up. Okay, so you'll see that equilibrium is a very important concept as far as geomorphology is concerned as such. Now, what is fluvial equilibrium? Okay, continuing with the same discussion, you'll see that you would have a recent upliftment that you could see in the top diagram here. Okay, and you have say you have a lower ground at at the same point as such, and you have a distance that needs to be covered between these two. Okay, what happens? Okay, you'll see that weathering, mass wasting, and other types of erosion, okay, will start eroding this particular rectangle here, and they'll carve out the material. So this is eroded material. This will start moving. Okay, not all of it will immediately move. All forces of physics are going to operate on this transportation, and initially a very small amount of it is going to be reaching the area of deposition. But as time passes, you'll see that the headlands, okay, will recede, and both erosion and depositional rates will decrease, because now it is coming towards a balance. Okay, but it still happens, and eventually what is going to happen is all this is going to be plucked off from here. It's going to be transported, and it's going to be deposited here. So what was a relief up and what was a relief down in a particular area tends to be equalized out in the whole process. And that is what is happening around us in various agents of erosion. It could be river, it could be glacier, it could be wind, it could be groundwater, it could be sea waves. Okay, they are doing this. They're trying to erode anything that is above the mean sea level, basically because that is the base level of erosion. Anything above the mean sea level is going to be eroded, and it's going to be attempted to be put down into the level beneath it. Okay, if you're going to have area to accommodate that, then it is going to be pulled down there as such. So this, in short, is the fluvial equilibrium. Okay, so you'll see that this is what Davis refers to as the young stage as such. Okay, and then of course you have the mature stage, and then the latest is going to be the old stage of a river as such. Okay, so these are things which are happening as such. What is a base level? As I've already said, base level is the level below which erosion cannot occur, okay, and above which deposition does not take place. Okay, now what you see as deposition is a temporary arrangement that nature makes around us. Okay, as I said earlier, also sea level is the ultimate base level. Of course, there are say some transit base levels, I would say, particularly as far as wind erosion is concerned. For wind erosion, sea level is not the base level. Okay, you'll see that local groundwater is the base level of erosion as far as wind is concerned. For all others, you'll see that sea level is the base level of erosion. An obvious question is, why is it that the sea level is the base level of erosion? The reason that you have the sea level to be the base level of erosion is because every other agent of erosion, excepting wind, every other is connected to water. What is the source of water? Oceans. So obviously, where will water try to get back to? Oceans. As a consequence, sea level or ocean surfaces is the ultimate base levels as such. Okay. Besides, as I said, lakes and reservoirs provide temporary base levels. Changes in sea level can be eustatic or relative. Okay, you'll see that sea levels can happen in a change in sea level do happen in a localized area, or they could happen on a very large scale also. So you have to keep in mind that aspect also, if whether this change in sea level is universal or whether it is localized, where what exactly is it, because you'll see that changes in base level may create and destroy accommodation space, in the sense that if the sea level rises, the processes will accommodate themselves accordingly. If the sea level falls down, the processes will again accommodate and adjust accordingly as such. So that's what base level means to us. Okay, this is a graded profile. Okay, you see that normally this is the smooth profile. You can see the same thing here also. Okay, this is the longitudinal profile from the head of the stream to the mouth of that particular stream. Okay, if you link points of altitude, okay, you should have a very plain say curve. Okay, this is called as the plane curve. This is also called as the longitudinal stream profile. I'm looking at the stream from the side. If I look at the stream, if I stand in the channel and I look at the stream, then I'm looking at the cross section of the stream. There could be various cross sections of the stream at various locations, but there is only one longitudinal stream profile as such. From the last of the points, the highest of the points that the stream starts, to the lowest of the point that the stream ends. So longitudinal profile, only one profile. Cross profile depends where you are standing in the stream, whether you are towards the mouth or whether you are toward the head. Okay, so you'll see that your cross profiles will look different. When you're towards the mouth, it will look a trough shape. When you're in the middle course, it will look U-shaped. When you are in the top area or the upper areas of the river, then the valleys will look V-shaped. Okay, what I'm referring to, a cross profile, is nothing but the valley shape of a river, cross profile or valley shape of a river as such. But since here we are speaking about graded profile, you'll see that, just imagine that there is a river wherein some part of that river is above the profile and some part of it is below the profile. Okay, if you take that much part out, okay, what is going to happen is what happened here. Okay, I say what we looked as a general curve here is this line here, and what is above that line is here, and what is below the line is here. Okay, so what is above the line is going to be eroded, and it is going to be deposited in locations just below the line as such. Okay, so that is how. Okay, here you can see how it changes. Okay, anything that is above the line, this dotted line is the general profile. This is also called as the graded profile. Okay, this is a hypothetical condition, by the way. No river in the world runs at this particular. There could be moments, minutes, a few hours, possibly in a particular location that the river could be graded, but the whole river cannot be graded, basically because the point at where the river starts is above the mean sea level. Consequently, there is always going to be an attempt of erosion. But as far as this graded profile is concerned, everything that is above the graded profile is going to be eroded, and it is going to be deposited in areas where it will fall into the areas which is below the profile as such. Now, why does this displacement take place? You can see here that there has been these arrows here. What do these arrows mean? These arrows mean that there has been some folding, some faulting, more to say, not exactly folding, but some faulting. You see that land surfaces have moved up and down, and because of that, the whole thing gets disturbed. And once it gets disturbed, you'll see that erosion will restart, and deposition will occur. And why does this occur? Basically because it has to eventually come to this particular line. That's the base level of erosion. Okay, and eventually you will have a new longitudinal profile at the process of erosion. Okay, you'll see that these various shapes of deltas that you can see, it's basically a battle between two different environments, the fluvial environment and the marine environment. Okay, you'll see that they'll try to again, there is this word inequilibrium is important. As long as there is this inequilibrium, there's always be this conflict between these two different environments, the fluvial environment and, as I said, the tidal environment or the marine environment as such. So yes, a lot of things do remain. Geomorphic processes continued. What is all this about? We are going to go into the details of that. We have not been able to cover all this today, but yes, by tomorrow we should be able to cover all that. But what all we have done today is a brief history into how geographers had been looking into it, the concept of equilibrium, what exactly equilibrium means, how what is base level, how base levels change as far as the profile of a river is concerned, when these change, what exactly happens as far as the river is concerned. And then of course we have earlier spoken about the various scientists who have been working throughout as far as the development of geomorphology is concerned. The older ones, it's Herodotus, etc., to the modern ones, Hutton and Davis, and of course the other ones. Okay, and the impact the theory of origin of species of Darwin has had on Davis as such. So this is the fantastic world of geomorphology. And of course, we spoke about the scale. As I said, this is a very important slide for you all. Okay, so we have done a significant thing as far as the entry into the geomorphology is concerned. Tomorrow we'll finish up with the rest of these aspects as such. Um, I'll stop sharing here and I'll return back. Yeah, there are a few observations which we have missed while we have off the screen. Mission Impossible, The Fallout, yes. Possibly that's the movie, I'm not very sure, but since Akshata says so, it may have been. Or Prachi says it's Ghost Protocol, I don't know which one of them. And then you have a very famous question that students always come up with. Achal says that, sir, can you share this PPT on the group? Yes, Achal, I am going to share this PPT on the group as well. But before I share and before we stop for the day, if you have any queries, if you have any questions, you can please ask those questions and I'll try to answer them. Okay. You can write down your questions. You can type your questions here. I'll wait for a couple of minutes before I close today's lecture as such. We thought about, we spoke about constructional and destructional forces. You'll see that constructional forces. Okay, now the Earth looks at construct. If you were the Earth, how would you be looking at construction? Obviously, the construction would be construction of land, the crust as such. Who leads to construction in that particular sense? In that particular sense, remember that volcanoes and earthquakes will. What did Dashrath say? Dashrath is saying something. I don't know what Dashrath has to say. And Avinash also says no. I don't know what no is this. I forgot the context of the question. Possibly I've asked earlier. But yeah, as I said, anything that's going to form the crust, anything that is going to form the crust will be constructive for the Earth, isn't it? If the Earth is supposed to be living in the terms of Darwin as such, in that case, you'll see that earthquakes and volcanoes will lead to construction. On the other hand, you'll see that as far as a river is concerned, as far as air is concerned, as far as glacier is concerned, what do? They polish off the surface, isn't it? Rivers, okay? Okay. That means no questions. I'll just take a couple of more seconds and then I'll stop for the day. So you'll see that a river or a wind or a sea wave or groundwater or a glacier, all they do is continuously they scrape the surfaces as such. So they are destroying the surfaces. So all agents of erosion are called as destructive. All agents of formation are called as constructive. So earthquakes and volcanoes are constructive forces. Folding, faulting are constructive forces. On the other hand, river erosion, glacial erosion, wind erosion, sea erosion, all of this is destructive. Okay, you'll see that human beings look at it exactly from the opposite point of view. For us, you'll see that as far as a earthquake is concerned, as far as a volcano is concerned, it is supposed to be destructive basically because it destroys life and property as such. But remember, it is performing its own duty as such. On the other hand, as far as a river is concerned, when a river floods and it erodes, and of course when it brings about say a floodplain, and when human beings cultivate those floodplains with agricultural practices as such, and they grow a lot of food on that, is obviously going to be something productive for human beings, but that is destructive for the nature as such. Of course, we'll go into the details of this when we meet for the lecture tomorrow. For now, we'll stop here. The next time we meet, uh, we will continue with understanding geomorphology the way we have been doing today. That's all for today. Stay home, stay safe.